Okay, cool. So peer-to-peer networking. So what are we going to talk about? So we want to talk about the network layer and kind of the network conditions that blockchains operate on. I put mostly there because there's a lot of blockchain words out there that maybe they don't operate on the traditional network structure that you would think. But I won't go too much in that. We'll talk about traditional like Web 2 overlay, and overlay being like a node mesh. Kind of the pros and cons versus the like Web 3 network overlay, the one that we choose. We'll talk about some attacks, how to address those, along with kind of like what is the threat model, and then libp2p. So, and I do just want to forewarn that like there's a lot of potential scenarios that can happen here that probably your mind will spur and say, well, what happens in this scenario and that? And I might not be able to get to all of them because I'm not like the absolute P2P networking guru. I do have somewhat of a networking background, so I think enough that we can jump into kind of some cool depth and talks. So let's get started. So centralized versus decentralized networks. Kind of want to weigh some of the, maybe the advantages and disadvantages to both. Yeah. Or maybe just the advantages to the decentralized one and then maybe the cons, which could kind of imply that the other one might be actually better at one. So first one is that there's no privileged nodes in peer-to-peer networks. So you have no single node or set of nodes in the case of like a content delivery network that have access to all the content or files or data that is critical for operating the network. So each node kind of has its own copy of the data. It's like its own replica, which is a really nice property. And I'll show you kind of why when we talk about some partitions that can happen. So another thing that you have is you have less bottlenecks when it comes to bandwidth. So like there's no central node carrying like all the load traffic. So you know, this is nice, right? Like there's not like just this single bottleneck, which we'll kind of show later is kind of makes it more vulnerable to attack as opposed to the more decentralized networks. DOS resistant or denial service resistant. So because of that, it's kind of difficult to overload the network with traffic because not a single node really is so critical towards the operation of the network. And then there's no centralized infrastructure typically needed. It depends on what the requirements of the blockchain are. And I put kind of a caveat here, except for the internet, which is still a centralized infrastructure. And I won't go too much into the philosophy of that, but I think we can see with countries where they just turn off the internet, we're kind of in trouble when it comes to peer-to-peer networks, if that is the case. So another thing to kind of note is that although like nodes operate traditionally, I won't say, a lot of node operators choose to run on a centralized cloud compute platform. It's not mandatory. You can run your own node typically on a laptop even. Maybe you don't want to. Maybe you don't want to stake too much money on that node because of, you do what you want, but it is possible.
And in theory, you could build a whole network with Bluetooth, just not your phone and your earbuds, but like a phone with another phone and just a whole network. We could connect, in theory, all of the academy with Bluetooth and create a decentralized network, right?
Yeah, so theoretically it's possible, yeah.
Okay. Okay.
Yeah.
So in theory, we could build a blockchain that do not rely on internet. Just in theory, like, obviously we cannot do it now.
Yeah, I don't know if you're running a bunch of nodes in like Africa though, and then some peer needs to talk to somebody in North America, how you can achieve that through a Bluetooth connection. But maybe there's some satellite that I don't know, depends on what the scope of the decentralized network you want to be.
There used to be a project that would allow you to download the Bitcoin chain via a satellite link. I don't know if that's still continued, but of course one way. But at least you could stay up to date with the current state.
So we could share malicious resources. That could be bad. That could be really bad, certain things. I guess I'll leave your imagination to what that could be. Latency. So we talked a lot about block production, and we talked about finalization via Grandpa. So latency may be an issue if we need to wait for many peers to receive the data produced by a single node, since everyone may not have a direct connection all the time. So in order to propagate, as opposed to if we're all just talking to a central server that we all have a connection to, maybe data is pretty easy to propagate in that instance. But in our case, we have some potentially added latency. There's difficult to regulate illicit activity. Yeah, I think that's kind of self-explanatory. There's no central point to go and snoop all users' data, for better or for worse. And then we have the network is limited by the nodes with the weakest hardware. So we're going to learn this more in the substrate and further, but when you actually want to run these nodes, we're generally looking for a minimum threshold of compute and network throughput, because if, for instance, since we talked about consensus before, if we actually want to reliably be able to talk to one another within a particular slot, say a block time of 6 seconds, then we need some minimum threshold to achieve that when it comes to network throughput and compute. Okay, initial discovery. So one thing with the kind of decentralized networks that we're talking about, we have this concept of being able to discover the network initially. And one way that we have this is like a boot node or boot nodes. And I'm going to touch on that like a little bit more in detail further. But essentially, you need to know somebody who's involved in this network. Otherwise, I can't really discover it very easily. Hopefully, that's pretty self-explanatory. Okay, so I want to talk about gossiping just a little bit. So we have this kind of mesh here. Node 1 has a direct connection to node 2 and 3. And node 1 has this block 45 that he's trying to share with the rest of the network. So what kind of the naive approach would say, if I want to propagate this information, maybe I just send it to everybody I have all the time. That might seem kind of wasteful, right? So in kind of this gossiping scenario, we would kind of do something like this. So we would actually ask our neighbors and say, hey, node 2 and 3, do you have block 45? This is kind of like advertisement or advert. And node 3 might already have block 45 and say, yeah, no, that's okay, you don't need to send it to me. And node 2 might say, yeah, I don't have node 45, can you send it over? And if you imagine this kind of happening at every stage of the network, you can propagate this thing or disseminate it across the whole network. So next, discovery. So we have a bunch of peers in this network, and we want to connect. So this is kind of the general process that can be used. So we connect to a peer, maybe via the boot node scenario. We ask a peer for a list of their known nodes, and I put addresses to fill in this distributed hash table. I'm going to talk about it just a little bit later. So just, I guess, for now, just think of it as just a registry of all the other nodes that you can access. We connect to a random subset of the peers from the list, and then we can repeat steps 2 and 3 kind of over and over again as we get more connections with new nodes and more peers. Cool. Partitions. Yeah, so we have kind of these two networks. So I'm trying to show the more centralized infrastructure here, but this isn't exactly, right? Like even in a Web2 framework, that master node in the middle, there might be multiple master nodes and they might sync with one another. But you could kind of think it as like, in this scenario, all the green nodes don't have the same privilege as the beige node. And in the scenario on the left, all of these nodes that are in pink, even including the green one, I'll talk about it in a second, they all have the same privilege. So what I kind of want to show you is you have these two like node layouts, And we kind of want to show like what happens when some nodes go offline, or maybe they get taken offline, or what is the case? How can the network still operate? So in the bottom left, this kind of top node and left node, they go offline. And from the green node's perspective, it's still able to kind of operate via its other kind of pathway here, right? So again, it has another node which it can talk to. The network can continue. And on this kind of right side here, the green nodes, if they kind of get partitioned from one another, well, they only have one connection, right, to these kind of like centralized privileged nodes. In this scenario, right, again, this is not, in every scenario, they might have multiple beige nodes that they have connections with, but just for simplicity, we're kind of looking at this privileged node, non-privileged node scenario. So the green node's kind of screwed if they lose the connection to the privileged node. Okay, so, and then we have, of course, this situation. The privileged node goes offline and nobody has access to the privileged node. These green nodes are just kind of left sitting there and they can't continue. Okay, so some attacks. This is kind of a fun part. I meant to put kind of like a scary picture here, but I didn't have time. Okay, cool. Eclipse attack. So let's say that we have this, we're this green solid circle in the middle, and we go and we want to connect to the rest of the network, but we have all these red nodes around us as our peers. And those red nodes they're bad guys. So they want to get us. Yeah, this is basically kind of like this Eclipse attacks. Like all your peers are now malicious. And so what happens, right? This distorts your view of like a healthy, normal, honest state of the network. So in the Grandpa game, we kind of talked about like, oh, what happens if everybody's just telling you lies about votes and you get all this kind of conflicting information, or like your view of the actual state is actually incorrect. Yeah, this is why we do depend on having some healthy connections to some honest nodes. So, so this green node is in trouble, but these green nodes, like, they still have some good healthy connections. So like, even though they have some connections to this like malicious red one, they have enough healthy connections with each other to be able to suspect out that this one's like a malicious actor, basically. Cool. So there's a few ways that you can execute these attacks, and then there's some ways to defend against it that we use in various systems. So one is you can actually flood a target node with a bunch of malicious peer addresses and say, hey, these are, I'm trying to connect with you, and I'd like to be a peer with you. And so the targeted node may just store these malicious peers and then like utilize them when they are going to resync or on like kind of their next boot up. So say you're a node and I know that I have all these peers, but then I go offline for some whatever reason, and then I kind of come back up and I check my peer list and say, okay, who can I sync with? If say someone just flooded my peer list and then I went offline and all I did was use the most recent peers in order to establish a connection with, I could be, depending on how many connections I want to make with my peers, I might be in trouble there. And so this kind of strategy is that you could flood the peer list with a kind of a bunch of malicious nodes, and then you could take that node offline and force it to resync with an incorrect state or an incorrect data. So some preventions against that. Yeah, so we want to be wary about new connections with other nodes. Now, that's not to say we don't want to take inbound connections from other nodes, but we want to be kind of careful and assume that people could be trying to mess with us, basically. So we could restrict inbound connections in some way. We also could do random selections of the peers that we connect with. So say I got flooded with a bunch of malicious peers, but then when I go to actually resync and start back up, I just take a random subset of my peers instead of taking like some recent or something or some very easily deterministic way of selecting my peers. Because if you knew how someone was going to select their peers, then you could probably do some interesting tricks to try to fool them, right? And try to take advantage of that. So adding some randomness allows you to kind of add some resilience. And then there's another way, boot nodes, which I talked about, which is like these deterministic node selection. So we kind of consider boot nodes to kind of have like more like higher credibility and trust, which can be kind of a bottleneck if you only have like a small subset of boot nodes and everybody's trying to bootstrap the network based off of those nodes. So generally, you want to rotate the boot nodes as well because they are also subject to those same attacks. But they generally have higher credibility. And I think when it comes to parity, substrate, we like publish the boot nodes and sign it.
If you download like a Polkadot binary, for example, and you run it, there's actually like this thing called a chain spec, which you'll learn a lot more about later this week. But it includes a list of boot nodes, and since it's part of the software release, it's signed just like all the source code and everything. So yeah, it's a little bit more older school trust model, but you're like, well, I mean, I'm already trusting Parity to have written this entire implementation correctly. Or maybe you're not trusting, you're like looking at the code, but like, you know, you have this cryptographic guarantee that at least this is who Parity says are the honest boot nodes.
Okay, so libp2p. So libp2p, basically toolbox for developing systems for peer-to-peer networks. And yeah, you can do some really cool stuff. So it's helpful in establishing encrypted and authenticated channels between two peers. That's really the use for it. And we use this in Substrate. Okay, so some difference when it comes to like addressing in libp2p and this peer-to-peer world. So it's kind of like you have this thing called a multi-address, and it's like a generalization of an IP address. This is a nice quote. This is actually from Pierre, who's like the networking guru in the Polkadot ecosystem. So he said a multi-address is to an IP address what a transport is to TCP IP. Transport meaning like TCP, UDP, QUIC, these, yeah. So here's an example. You have this IPv4, which tells you this IP address format, localhost with a transport of TCP, and here's the port. But there's other formats that can be in here. IP6, yeah, you could put UDP in there. There's a WebSocket, so yeah. Has some more information bundled in there so that maybe not only do you need maybe not only do you have the information to reach a peer, but you also have the ability to open a TCP connection with them as well inside of that, which might be useful. Protocols. Okay, so yeah, so you can negotiate your protocols in libp2p, and so you can actually exchange your encryption protocol via this kind of like negotiation process. So these protocols have their own like identifiers, and you can basically, when you're doing the setup of a connection, you can say like, hey, what are we going to use for encryption or transport? There's ping, so basically you can, you know, check, just do a liveness check of your peers to say like, hey, are you still around? Are you still live? Check if it's online, and then like this identify concept in libp2p, which is just like peers exchange information about each other, such as like public keys and known addresses. Yeah. Okay. I can never say this word. It's like Cadelmia, but yeah, I can never say this word. So that's what KAD-DHT. So DHT is standing for distributed hash table. This is what I'm going to say on this. There's some complexity here, and I'm going to leave the resources to really dig into this. I'm not going to be able to answer every question about it for sure, and it takes some time to talk about this topic. But I'm going to give an overview, and yeah, hopefully that's sufficient for what we got. So simply put, it's like this hash table containing a set of data entries, and these data entries are distributed across the network. So there is no like central registry that we have where to like obtain all the information of who are all the peers. You know, say I have a peer who's way over here, and I want to open a connection with him. I can't just like go to some server and say, hey, I want to open a connection with this peer. I need to kind of maintain like peers locally and where to access content. And this, this table basically gives you a distance metric of where you can find certain items. It works on this thing like this content-based addressing concept where maybe I don't just say, hey, I want to go to this node and I want to retrieve this data. Instead, I just say, hey, I want to retrieve this data. What are the, and this gives you a way to compute what's the distance to that data. So nodes will have a certain a logical, this isn't like actually like I go walk 10 football fields and I get there, but it's a logical distance that's determined. Okay, so here are some of the operations, and hopefully it could make a little bit more sense, and I got a picture. So this is directly from libp2p. So you have this find node operation, which given some key, you'll find the closest nodes to the key. So again, I would say key is like block 42, just for an example, right? And so I'll find the closest nodes to that key. Put value, so I'll actually add a key value mapping to this table. For instance, block 42 and the actual data associated with it. Get value, so given a key, I retrieve the value, pretty simple, similar to most hash tables. And add providers, so advertising in the network that a peer is providing a given key. So like, hey, I'm gonna provide block 45 to the network. And then get providers, you know, find out what peers can provide the value for a specific key. So it's like, maybe I know 3 people who can provide this data for me. Okay, so just this quick example, and this is not necessarily how we use, or how, I'm just gonna say CAD, I can't say Cadelmia. But it is one way that you could use it, right? So say I wanna find, I have key block 45, and I want to find where should I get that. So this is me in the middle, and I can kind of see that peer 3 has a distance of 5 to this key. Cool, all right. Works. Okay, peers. So there's these kind of 3 things that are commented here. You have a peer ID, you have peer info, and you have a peer store. This isn't actually how the struct looks in libp2p, but I just like made one up based on what it actually is supposed to represent. But here on the top, you have this peer ID, which this would be actually the P2P address. But what's nice is you have other info again. So if I wanted to open up a TCP connection on port 4242, I could do that, because I have this kind of in this peer ID encapsulates this multi-address information. And then you have this peer info struct where you have some peer ID, or peer info. You have a peer ID, and then you have other multi-addresses, which are kind of like listening. So this others would be, like a type, like a hash set, or it's a set, right? You don't want to have duplicate pairs. And then you have, set of multi-addresses a particular peer is listening on, is this other multi-addresses. And then the peer store is basically a table of peer keys and addresses and some associated metadata, kind of like an address book. I don't even know if there's address books anymore, but it's kind of like a universal address book for the whole network. Stream multiplexing, I'm just going to briefly mention it. So you have a libp2p connection. You can have multiple streams, just like most sockets, right? You have different ports. Say I'm connected to IP address XYZ, but I want to have multiple data streams that go through this connection. So it supports this, thankfully. Okay, so security maliciousness. This is, again, the fun part. So from game theory, Just because a particular type of attack is theoretically possible or feasible does not mean that it's practical. So we'll talk about some attacks that, again, you can do, but maybe we can think about if they're practical or not. Okay, so there's some important things to kind of notice here, like when we're dealing with kind of like the vulnerability of these like peer-to-peer networks. So we have this identity and trust. So every node has a public-private key pair or peer ID. I mean, yeah, we said peer ID is a little bit different, but anyways, you have a public-private key pair, so you sign stuff. So this allows us to verify who we're talking to when we're trying to think about this kind of malicious game. And then this one I thought was important. Like, authorization is not default. And what I mean by that is, like, some systems may not require any authorization to join, right? Like, I don't know, like Joshy's just some random guy and he wants to join, and I don't even need to like see his credentials. I'll just say, all right, sure, I'll open a connection with you. So you can, I kind of like to think of this as like a tuning of the permissionless, yeah, whatever. Tuning permission to the network, right? So if you think of it in the extreme case, I just say like, no, you need to pass this very high bar to talk to me, and just anybody else who tries, you know, I'm not going to talk to you. Or I can scale that back and allow more people to join the network with looser credentials. There's reputation systems, so this is good. Yeah, there's a chance that our peers are, again, lying to us, as the kind of we saw with like the Eclipse attack and stuff. And so what we can do is, like, if people are just consistently giving us faulty information that we determine, we can like blacklist them. We can just say like, I'm not going to listen to this person anymore. Or we can even get more granular than that, and we can just like lower their scores and say, I'm going to just kind of maintain connections with more reputable nodes because I know that they're not going to try to trick me. So yeah, some things that could be malicious from other nodes is like they're just like sending you the same information over and over, even though you don't want it. And yeah, so we want to try to maintain connections with nodes that are reputable, but we want to add in some randomness so that we like allow new nodes to join. Because like if you think about it, if we had a reputation system where you start at 0 and you know. And I have reputation with all my peers and it's like 100, then I'm just going to say like, I don't want to accept you, you know. But we want to throw some new nodes in there so that we make it joinable and not too exclusive to newcomers. Did I finish that? Yeah, I did. Okay, so denial of service. So these distributed hash tables are vulnerable to Sybil attacks, like many different things. I'll talk about just a little bit why. So querying. So a query using the approach that we kind of talked about, like finding, again, block 45 as a means of content, may need to be routed through several peers before the query is fulfilled. So those peers can be malicious and attempt to lie to us. So if we have enough bad actors in the lookup path, then that's also an issue. So how could you do that? I'll kind of explain that. So say I don't want anybody to get block 42, and I can kind of like target that specific key. And because I have this distance metric, so I can like kind of identify who's around this particular piece of data that I don't want anybody to get, and I can spin up a bunch of nodes that have that same calculated like DHT metric to those nodes. So if, yeah, I guess I kind of explained that. Yeah, and you do this by generating IDs close to the target key. Cool. Sybil attacks. Yeah, so Sybil attacks are hard to defend against, and precautions can be taken higher level to help mitigate. And so I'm hoping that since we went through a lot of consensus, we can identify like what methods we have in blockchains for filtering out nodes that are really being malicious to us and lying. Proof of work being one of them.
What is a Sybil attack?
This is like basically like flooding with like malicious nodes or malicious actors in kind of a situation. So if it's very cheap for me to basically replicate a lot of actors in the system, then I can kind of flood the system and overload it with more bad actors than good. I don't know if that's a formal definition, but that's the definition that I have in my head. Yeah. So I left some additional resources here. This is like the libp2p documentation, where you can read a lot more about very specific things if you're really interested in the networking stuff. And yeah, any questions?
In one of the slides, you mentioned that there is not validation, like you give a grade to the peers. Like
Yeah, reputation.
How do you call it?
Reputation.
Yeah, reputation. Does this apply right now in the network? And if yeah, in the blockchain network?
Yeah, like in Substrate, we use reputation. According to Pierre, I trust him. Yeah, we do.
Yeah. Okay, thank you.
I know that there is a paper on IPFS,
Right.
the system that also uses lib peer-to-peer.
Yeah.
That showed an Eclipse attack on IPFS. They used kind of a bug in lib peer-to-peer as well. And I think they showed it was a couple of €1,000 or dollars to attack the whole network, eclipse the whole network. And they also have some cost-based analysis on how expensive it would be to perform the attack without the bug. And I think you can sort of use it as well on Polkadot to approximate how much it would cost to perform an Eclipse attack.
So it seems like most of the architecture you propose was dependent on the bootstrap node. Like, as long as these collection of nodes are legit, then the network can find other peers. What if you were to bribe the bootstrap nodes or some of them to have another list of malicious peers in that case?
Yeah.
What
I
would
love where
happen
this is going. This is perfect. Yeah, I mean, it's a valid point. And so what would be, the logical defense in your mind? Maybe increase the number of bootstrap nodes, maybe rotate the peers that they're talking to, and maybe rotate the actual boot nodes themselves that get published. So I don't know if there's, just remember, I want to join this group of people who are communicating. I have to at least know a person. It's it's like Inception. I don't know. You got to know at least somebody, or else I don't even know it exists. So that's kind of the issue now. I'm sure there's ways that they're trying to address it, but that's one way that we do. So, anyways, yeah.
Thank you.
Thank you. All right, that's it.